the third unit, that is the continuous beam. What is its importance and why we will consider more care about the continuous beams. So why? Because all civil engineering structures associated with the continuous beam. Here these are the different types of the continuous beams. These are some of images of the continuous beams. So this is why we will consider, that is only reason they will accommodate less bending moment and occupy more loads. So that's why we will consider continuous beams compared to the simply supported beams. So in case of throughput cantilever, we will assume RP, vertical reactions are the redundant. But if we can follow the same procedure in continuous beam, that will be very difficult. So that's why we can assume redundants are support moments. So that is moments at the endpoints. So now we will go to the three moments or Clapeyron's theorem. One scientist introduced the three moment equation. His name is Clapeyron. So now he is the scientist. Now we will see the different types of the continuous beam. The first one is two span continuous beam with one end fixed, one end simply supported. If you take the second one, two span continuous beam, both ends fixed. Third diagram, two span continuous beam having overhanging, one end is the fixed end. You see this is three span continuous beam, one end is fixed, one end is simply supported. So these are the different types of the supports. Now we will take the derivation. So now all of you see, if we are cloud, any disturbance?
No, sir.
Okay. So now all of you take the derivation. If we are strong in the derivation, then the problematic will be very easy. So all of you take the problem. This is two span continuous beam subjected to some arbitrary loading. So here I will consider LL, length for the left portion, LR, length for the right portion. Now if you see there are three support conditions. Now if you see, there are three simply supported conditions. As from the basics, at simply supported ends, the bending moment is zero. The bending moment is zero at the end points, but the bending moment at this point is not zero. Even though it is the simply supported beam, it is connected between the 2 points. Definitely there will be a chance to movement. So one important point, if all three are the simply supported, as per the basic knowledge, when there is a simply supported end, at that case the bending moment is zero. But in case of middle portion, the middle portion is combination of the two members. Here the bending moment is not zero. At the end points our bending moment is zero. So now all of you take the second diagram. Second diagram, deflected shape due to the applied load. The theta CL, deflections due to the applied load on the left span, theta CR. All of you take the diagram. Now here I will introduce moments ML, MC, MR. Out of these three moments, ML equal to 0, MR equal to 0. Someone have the doubts? Sir, initially that is the simply supported. You are saying simply supported moment is 0. But why again you will show ML? So why? Because in case of three moment, we require three moments. While substituting the ML equal to 0. That final ML goes to the 0. There is no problem. So at L, the moment is 0. But I will introduce some ML. But finally in the equation, I will consider ML equal to 0. Don't confuse that. So all of you take the deflected shape of the continuous beam, theta CL, theta CR. Now, all of you take this theoretical description. First point, consider two adjacent spans of continuous beam. Don't worry, all of you take notes. Consider two adjacent spans of continuous beam are shown in figure ML, MC and MR. That's enough. Is taken to different for different spans. In the present case, IR. So IL represents the moment of inertia for the left support. IR represents the moment of inertia for the right span. Now LR, length for the left span, length for the right span. I request all the members write down the theoretical description. IL, moment of inertia for the left span. IR, moment of inertia for the right span. LL, length for the left support, length for the right support. Go to the directly fourth point. This is relation derived from the tangent to the elastic curve is horizontal. Now theta CL plus theta CR equal to 0. What that indicates? The tangent at that point is horizontal. Theta CL plus theta CR equal to 0. Before going to the derivation, we know the each individual terms explanation. ML, MC, MR, IL, IR. Now we will take theta CL plus theta CR equal to 0. Now, so now all of you, మీ డయాగ్రామ్ ఇలా ఉండాలమ్మా ఒకే షేప్ లో. నాకు పాసిబుల్ లేదు కాబట్టి నేను స్లైడ్ బై స్లైడ్ వచ్చాను. ఇన్ ద ప్రీవియస్ డయాగ్రామ్ we have up to now we can complete. Now from this below you can indicate this diagram. Bending moment due to the applied load. So all of you very careful about XL, XR. Now we can draw the bending moment due to the applied load. AL, area upon the left span. AR, area upon the right span. If you observe XL, XR, so that XL and XR measured from the outside of the span, not inside of the span. XL, in every problem we have to calculate AL, XL. AL we can calculate depending upon the area, sorry, shape of the diagram. XL, it is measured from the outside. XR, it is measured from the outside. The final XL and XR measured from the outside. So after you complete this diagram, hello.
Yes, sir. Completed, sir.
Right. Next, at the bottom, you can write bending moment due to the support moments. This is another bending moment diagram due to the support moments. ML, moment at the left support. MR, moment at the right support. MC, moment at the middle point. Now this is another bending moment diagram. This is for the support moments. Previous one is due to the applied loads. ML, MR and MC. These are the support moments. This one is due to the applied loads. Now all of you observe. So now if I want to write theta CL for the left portion, if you observe in the case of theta CL, so this is one area, this is second, this is third. If you take right portion, so this is fourth one and this is fifth one, this is sixth one. Now if you see the diagram, for the left portion there are three diagrams, for the right portion there are three diagrams. If I want to write the compatibility equation, theta CL means nothing but the deflections. In case of deflections, we can blindly follow area multiplied by the X bar. For theta CL, how we can write that deflections? First one is the AL, that is the area multiplied by the XL for the first diagram. Area multiplied by the distance. If you take the second diagram for the left portion, second diagram, that is right angle triangle, half into, that is ML into base. Base is LL. Don't confuse. For the left portion, there are three diagrams. The first one is AL into XL, area into X bar. If you take the second one is the right angle triangle, half into ML, maximum ordinate, and base LL. What about the centroidal distance? Centroidal distance ఎంత అవుతుందండి? That is from the base is 1/3. If you take diagram 3, its area is half into MC, again base is LL, its centroid from the ML is 2/3 of the LL. So that is for the left. Now if you go to the right portion, theta CR, AR into XR, if you take the sixth one, half into MR into LR into, from the base, the distance is 1/3 of the LR. If you take the fifth area, half into MC into LR into 2/3 of the its centroid location. For the diagram 3 and 5, its centroid location is this is its centroid location. So this is 2/3 and this is for the bottom one is the 1/3. Now we can write the equations. So now here you can write the actual bending moment diagram on span LC is broken into two parts. After completion of the two diagrams, now you will write the bending moment diagram on span is broken into two parts. The first one is due to applied load on span, due to applied load. Second one is the due to support moments. Here you will write the above equation AL and AR, AL and AR, area of the bending moment diagrams due to the applied loads on left and right span. Each word explanation is very important. AL, AR, area of the bending moment diagrams due to the applied loads on left and right supports. Now if you take XL, XR, XL, XR, representative CG, center of gravity, distance from the left and right support respectively. So AR, area of the bending moment diagram on the left side, AR, area of the bending moment diagram on the right side, XL and XR. Is it clear? मैं और कौन डाउट्स है उन्होंने एक बार को?
No, sir.
So one or two members are responded quickly. Then what about the others? If you are going like this, then when the next class I will achieve. That means 30% video on just live lo unnara leda. I will allot to some other faculty. If you quickly respond, I don't go to that such type of situation. So moreover, in the so many years they will ask the derivation. Derive the Clapeyron's theorem. Derive the Clapeyron's theorem. Next, now theta CL plus theta CR. All of you write. The rotation left support C, theta CL, and rotation of the support C, theta CR can be calculated from the moment area method. Now directly you write theta CL equal to, now directly I will go to the theta CL. How we can calculate theta CL? That is from the moment area, force multiplied by the perpendicular distance. So theta CL equal to deflection of L from tangent drawn at C, L, L dash. So where that bottom moment by M by EI diagram between C and L about L. The second point is important. M by EI diagram. So we can hear that M by AI diagram in case of the cantilevers. First, we can calculate moment divided by the EI. So, why we divided the EI? According to Moore's theorem, if the moment is in terms of the M by EI, then we will apply the Moore's theorem 1 and 2. So, now theta CL, here IL, moment of inertia for the left span, by LL, length of the left span. Now, we have three areas, its centroidal distance. First one, AL by EIL. AL by EIL, that is the first diagram, into XL, its centroidal distance. That is the first. So now we can write theta CL. For the left portion, there are three diagrams. First, all of you write AL by EIL into XL. Second, you see, this is, I will consider, now this is my second diagram. What is its shape? Triangle. Half into ML by EIL into base length LL. Its centroidal distance is 1/3. Here I will mention. So this is for second diagram centroidal distance. If you observe that centroid is the from the base 1/3. Next, third diagram, half into MC by EIL into length of the member. Next, 2/3 of the LL. So that is for the third diagram. So very easy. Three areas, its centroidal distances. 1, 2, 3. First one is the AL into XL, plus second one is half into ML by EIL, length of the span, centroidal distance. If you take the third diagram, MC by EIL, LL into 2/3 of the LL. Now, if we can modify the above equation, the bottom one is AL by XL, EIL into LL plus ML plus LL by 6 EIL plus MC by LL plus 3 E by IL. So this is for the left span, theta CL. Now similarly, you can write theta CR. Similarly, all of you write the theta CR. Theta CR. That's very simple. Whatever we get in the same equation, AL replaced with AR, XL replaced with XR. The remaining equation will be the same. Now I request all the members calculate theta CR. So in the compactability, theta CL plus theta CR. I think all of you complete this portion, theta CL.
Yes,
Oh,
sir.
sir.
Okay.
Sir.
Those who are completed,
sir.
go to the theta CRM. Complete అయిన వాళ్ళు go to the theta CR. Those who are not completed, please take down. Three areas, its centroidal distance. That's very simple. The same procedure we will adopt in the calculations of the problems. So in these cases, I request all the members, XL measured from the outside. I repeatedly mention XL. It is measured from the outside of the left span. XR. It is measured from the outside of the right span. Now, theta CR. Theta CR. Now, theta CR equal to IR by LR, moment of inertia for the right span by length of the right span. For this, AR by EIR. So this is 1 and this is 2, this is 3. Now again here there are three diagrams. First one is AR by EIR into X bar plus second diagram half into MR by EIR into LR into 1/3 of the LR. Second diagram centroidal distance. Take the third one half into MC by EIR LR 2/3 of the LR. And if we can modify AL XR by EIL LR plus MR LR 6EI IR plus MC LR by 3E IR. Now we have the P equation, Q equation. Substitute these two equations in compatibility. Theta CL plus theta CR equal to 0. Theta CL plus theta CR equal to 0. On the left of the span, 3 areas, its centroidal distance. On the right of the span, 3 areas, its centroidal distance. Now we will equate, we will get to 0. Theta CL plus theta CR equal to 0. Now this is my final equation. Theta CL plus theta CR equal to 0. All of you, theta CL plus theta CR equal to 0. Try to modify, you will get some final equation. Theta CL plus theta CR. If we can simplify equation R, we will get ML LL by IL plus 2MC LL by IL plus 2 LR by IR plus ML into LR by IR equal to minus 6 ALXL by ILLL, and there is some mistake again, that is also minus 6 ARXR ARXR by so now you take this equation, very small mistake in the previous equation. First you can all of you add theta CL plus theta CR equal to 0. From that ML LL by IL plus 2 MC LL by IL equal to minus 6 AL XL by IL LL minus 6 AR XR by IR LR. This is IR. So when moment of inertia is constant throughout the member, then the above equation is modified as MLLL plus 2MC length of the left portion plus length of the right portion plus MR moment at the right span multiplied by the length of the right span equal to minus 6 ALXL by ILLL equal to minus 6 AL2, sorry 6, this is not AR, minus 6 ARIR divided by IR into LR. There is a small correction in this equation, don't blindly follow that. Minus 6 AL XL by IL LL is correct. Minus 6 AL is not correct. 6 AR XR by IR LR. So when we want to apply the moment equation, now this is the bottom equation, we can call it as the Clapeyron's theorem or the moment. If you take ML as A M R as P, and middle one is same. MA, LA plus 2MC, LA plus LB plus MB, LC equal to minus 6 AL XL minus 6 AR XR. Now, all of you take these three conditions. Now, in case of the Clapeyron's theorem, we have the three conditions. In case of Clapeyron's theorem,
Sir,
we have
voice break అవుతుంది sir.
the three conditions. Equation one, voice breakup. So all of you take three equations. Equation one, the basic equation. If the given problem has different moment of inertia, then we will apply the first equation. If the given, by observing the given problem, it has constant moment of inertia, we will apply the second equation. When there is a sinking of the supports, delta L or delta L, delta R, deflections at the left support, deflections at the right support, that is called sinking of the support. Then we will consider equation 3. The first fundamental equation will be modified when it is same moment of inertia. We will get the second one. When it has the deflections, we will get the equation 3. Equation 2 and 3 are obtained from the equation 1. If you thoroughly understand the equation 1, if it is constant moment of inertia, directly we can write the equation 2. Sinking of the supports, when they can give the span A sinks and 5 mm, span B sinks and 10 mm, then we will apply the equation 3, not 1 and 2. This Clapeyron's theorem we can apply any type of support condition. Either it is 2-span simply supported, 2-span continuous beam, 3-span simply supported, 3-span fixed beam, 1 end fixed, 1 end overhanging, whatever may be the given condition, we will apply these three equations. I request all the members, the first one equation is the varying moment of inertia. If the given problem span AB 2I, span BC 3I, then we will go to the first equation. When there is a constant moment of inertia, then we will go to the second equation. If sometimes they will ask the deflection at point A is 2 mm, 5 mm, then we will go to the equation 3. These are the three equations we need to calculate continuous beams. So now all of you write the three equations.
Completed.
Right, thank you. Now we will see what are the different types of the continuous beam. Sorry, before going to the different types of the continuous beam, previously for each unit we have some basic requirement. If you go to the proport cantilever, you should know the how to calculate cantilever deflection. Come to the deflections of the trusses, you should know how to resolve the concurrent force system along X and Y. So likewise, here are the some basic requirement. What is that? In the case of the continuous beam, first we can draw the free bending moment diagram. Free bending moment diagram means nothing but all ends are assumed to be simply supported. Now we can know if a simply supported beam is subjected to point load at midpoint, what is its bending moment? A simply supported beam is subjected to UDL over the entire span. What is its maximum bending moment? A simply supported beam is subjected to eccentric point load. What is its maximum bending moment? So here if you take the first one, when a simply supported beam acts at midpoint, so that load is P. Now the maximum bending moment is PL by 4. So whenever in case of continuous beam, they can ask free bending moment diagram. That means we can assume ends are the simply supported. If it is at the midpoint, directly we will calculate WL by 4 or PL by 4, or otherwise you go to the fundamentals, that is sigma Fi, RA plus RB equal to P. Now you take sigma MA. From that you can calculate what is the bending moment at P. So going on the higher classes, if you go to the bridge engineering, for one problem nearly we can use the simply supported or cantilever 3 to 4 times. For each time it is not possible to calculate sigma Fi, sigma MA. So you have to by heart. Whenever you see the simply supported, there is a point load, then directly we'll say that the maximum bending moment is WL by 4. Whenever you see the simply supported with UDL throughout the member, the maximum bending moment is WL square by 8, or otherwise you will go to the fundamentals. Now if you see the 2 point loads on one eccentricity. So for the next class, I request all the members gather different simply supported beams bending moment diagrams. So this is the bending moment diagram. Maximum bending moment C dash WL by 4. Now this is the step by step process that. Now we will see the diagrams. If you see the first diagram, my diagram కనిపిస్తుంది అందరికి? Hello.
Yes, sir.
If we observe the first diagram, right, thank you. The first, I can call it as it is continuous beam. Why? Because it has more than one span, more than 2 supports. Here 2 spans, 3 supports. This is continuous beam. How I can call it as continuous beam? Here 2 span continuous beam with 2 ends are simply supported. Both ends are simply supported. If we observe the first diagram, here they will not mention I value. So that's why EI is constant throughout the member. For the first diagram, 2 span continuous beam with 2 simply supported ends and constant moment of inertia. If you take the second diagram, if you observe the 1, 2, 3 span continuous beam and having the simply supported ends. So when we can say the continuous beam, we will see the what is its end condition. The continuous beams having simply supported ends. If you observe this diagram, for the first span, that is I, second span 2I, third span 3I. So this is the varying moment of inertia. So now this is 3 span continuous beam having simply supported ends and varying moment of inertia. Now if you see this diagram, first one is the 2 span continuous beams with one end fixed, one end simply supported. If you see the bottom one, are 2 span continuous beams with fixed ends. If you observe the bottom diagram, 2 ends are the fixed end. If you observe the bottom diagram, the moment of inertia is varying. So if you see the next diagram, this is 2 span continuous beam overhanging. One end is simply supported, other end is the overhanging. Bottom one is the overhanging with one end is the fixed end. Now in case of continuous beams, these all cases are comes under the continuous beam. So when you see the continuous beam, the first one you can see how many spans are available. So 1 or 2. If it is 2 spans, 2 span continuous beam, then you will see the support condition. So based on the support conditions, you will categorize the, if you take the first one, 2 span, continuous beam, and end conditions are simply supported. So the constant moment of inertia. If we take the second diagram, 3 span continuous beams with simply supported ends and varying moment of inertia. So now these are the different types of the continuous beams. Next class, what is the step-by-step procedure in case of Clapeyron's theorem? So any doubts in today's class?
No, sir.
So all of I request all the members once again see the derivation and at least calculate 3 to 4 simply supported beams with the different loading. I want to know the only maximum bending moment. I don't want to go to the shear force. If you see the simply supported beam with point load, what is maximum bending moment? WL PL by 4. So why? Because if you go to the fourth unit, there is another moment, that is the fixed trend. Don't confuse. So okay, all of you can